Okay, so in this video I'd like to look at finding derivatives of trig functions. So at the moment we don't know how to do that, but we do know in general, given a graph of a function, what its derivative should look like. So let's take a look at the graph of sine of x here. Suppose we want to sketch the derivative of this function. So we see that it's going to start at some point, and then here where the slope is positive, the derivative should be positive. But then where sine has this horizontal tangent at pi over 2, the derivative should hit 0. Then after that, the function is decreasing. But eventually it comes back up and has a horizontal tangent again at 3 pi over 2. And then after that point, the function is increasing again. And you can do a similar argument to see that it should look something like this on the left. And you can see that this graph that we've drawn, without really thinking about what it should be, ends up looking a lot like the graph of the cosine function. And this is no coincidence. In fact, it's true that the derivative of sine of x is equal to cosine of x. But in order to prove that, it's not enough just to look at the graph. We really are going to have to look back at the definition of derivative. So we're going to need two trig limits in order to calculate the derivative of sine using the definition. The first one is that limit as x goes to 0, sine of x over x is equal to 1. The second limit we'll need is that the limit as x goes to 0, cosine of x minus 1 over x is equal to 0. So I'm not going to go over how to actually find these limits, but you can maybe convince yourself of this by looking at the graphs of these functions, or by plugging in x values really close to 0 and seeing what happens to the output. Okay, so using this information, let's try to find the derivative of sine of x using the definition. So the derivative of sine of x is going to be equal to the limit as h goes to 0, sine of x plus h minus sine of x divided by h. Now there's a trig identity which lets you find sine of x plus h. So if you want to remind yourself of trig identities, there is a worksheet posted on the Sakai website that has a bunch of them listed. One of them is a formula for sine of x plus h. And if we apply that formula, then we get this is equal to sine of x cosine of h plus sine of h cosine of x. So that's what we get from applying that trig identity. Then minus sine of x, all divided by h. If we rearrange this a bit, we have a sine of x here, a sine of x here. So let's group the two terms with a sine of x together and pull the sine of x out front. Then we get cosine h minus 1 over h plus limit as h goes to 0, cosine of x times sine of h divided by h. Now if we look back at these limits that we had above, up here I used x instead of h, but of course that letter doesn't matter. We have a limit as h goes to 0, cosine h minus 1 over h. We've said that that limit is equal to 0. Similarly, we have a limit sine h over h. We've said that limit is equal to 1. So if we use those facts, we see that this does indeed simplify to cosine of x. So we can show using the definition, if we take these facts for granted, that the derivative of sine of x is equal to cosine of x. Similarly, the derivative of cosine of x can be found to be negative sine of x. And we can also find derivatives of other trig functions. So suppose I want to find the derivative of tangent of x. How can I do this? Well, I use the fact that tangent can be written in terms of sine and cosine, and we just figured out what the derivatives of sine and cosine are. So the derivative of tangent is the same as the derivative of sine of x divided by cosine of x. So we can apply the quotient rule to this thing. We have to take the derivative of the top, which we now know to be cosine of x, multiply by the bottom, which is also cosine of x, minus derivative of the top, which is, derivative of the bottom, which is negative sine of x, times the top, which is sine of x, over the bottom squared, which is cosine squared of x. If you simplify this, you'll get sine squared of x plus cosine squared of x divided by cosine squared of x. And if you use a trig identity, sine squared plus cosine squared is always equal to 1. That's the Pythagorean identity. So this is equal to 1 over cosine squared of x, which is the same as secant squared of x. So basically the idea is that for trig functions other than sine and cosine, you can always write it in terms of sine, cosine, then use all the derivative rules we've learned to find the derivative of these other trig functions. So similarly, the derivative of cotangent of x is going to be equal to negative cosecant squared of x. The derivative of secant of x is equal to secant of x tangent of x. And lastly, the derivative of cosecant of x turns out to be negative cosecant of x cotangent of x. So using these techniques, we now know the derivatives of all 6 of the trig functions, and we can use this in conjunction with the product and quotient rules that we already knew to take the derivatives of a much larger class of functions than we were able to before. So for example, we can take a look at something like the derivative of, let's see, x squared plus 1 over cosine of x, and we can calculate this using the quotient rule. So it's the derivative of the top function, which is 2x times cosine of x, minus the derivative of the bottom function gives us negative sine of x. The negative becomes a plus. We get sine of x times x squared plus 1 over cosine squared of x. Or just as another quick example, suppose we want to now take the derivative of sine of x times x cubed minus 4. Well, for this we would use the product rule. So then we'd have the derivative of the first function times the second, plus the derivative of the second function times the first function. And so we can calculate the derivative of this as well. So now basically, from what we've learned, we can now quickly calculate derivatives of things involving powers of x and trig functions, and then combinations of them through products, quotients, function composition, and so on. So knowing derivatives of trig functions, there's now a ton more derivatives that we can take easily without having to go back to the definition. So this is quite useful. And so in the upcoming lectures, we're going to look to expand that library of functions that we can differentiate even more. So we know how to do power functions, we know how to do trig functions. Things remaining to look at are exponential functions, logarithms, and inverse trig functions. And so those are all going to be coming up in upcoming lectures.